Reach out and touch something solid near you. The wall, the edge of the bed, your own hand. It feels permanent and finished and safe, and so does the dark outside your window and the quiet sky beyond it. That sense of a settled, trustworthy universe is the most comfortable thing you own, and tonight, very gently, we are going to take it apart. There are 10 ideas in modern physics that are real and published and quietly terrifying, and the reason you almost never hear them said out loud is not that they are secret. It is that no one quite knows what to do with them. Each one removes a certainty you never think to question. That space is smooth, that we are safe where we are, that matter lasts, and the worst of them, the theory waiting at number 1, is not about any object out in space at all. It is about the single thing you are most certain is still running this very second, and by the end of tonight you will know exactly what it is, and why most physicists would rather not say it aloud. Get comfortable. If you're the kind of person who loves having your sense of what is solid quietly dismantled, a quick like and subscribe genuinely helps this channel reach more curious minds like you. Because by the end of tonight, the calm sky you think you know is going to feel far less finished and far more precious. Now, let's gently drift into this. Space looks smooth. That is the first thing to let go of tonight. When you lie back and look up, the darkness between the stars seems like the most finished thing in the universe. It is even, it is quiet, it is featureless, and it asks nothing of you. It feels less like a place and more like the absence of one, a clean black sheet with a few points of light pinned to it. And that smoothness is the first of the things you never think to doubt. You do not question whether space is continuous, whether it is seamless, whether the emptiness between here and the nearest star is really as plain as it appears. Why would you? Nothing you have ever seen suggested otherwise. Tonight we're going to spend a couple of hours gently pulling those assumptions apart one at a time. There are 10 of them, and they are arranged as a countdown, from 10 down to 1, and each step removes a little more of the ground you're standing on. Not with fear, and not with noise, just with the slow, patient work of following the physics past the point where most explanations politely stop. These are real ideas, published in real journals by serious people, and the reason you rarely hear them spoken aloud is not that they are secret. It is that no one quite knows what to do with them. They are too far away in time to feel urgent, or too damaging to a favourite theory to dwell on, or too corrosive to ordinary certainty to say in a calm voice. So they get filed away. Tonight we're going to take them back out carefully and hold each one up to the light. We begin with the fabric itself, and with something that may be threaded through it that you cannot see. The idea is called a cosmic string, and it is not a string in any sense you would recognize. Imagine a flaw in space, not an object sitting in space, but a defect in the material of space itself, a place where the smooth sheet was folded wrong when it was first made and never relaxed back into place. Physicists think that if these things exist, they were created in the first unimaginably small fraction of a second after the universe began, in a stretch of time so brief that writing it out means putting a decimal point down and then walking 35 more zeros to the right before you reach the 1. In that first flash, the whole cosmos was cooling at a rate we have no words for, and when something cools that fast, it does not always settle evenly. You have watched this happen, on a scale you can hold. When a pond freezes over on a cold night, the ice does not form as one perfect crystal. It forms in patches, each patch settling in its own direction, and where the patches meet, they do not line up. You get cracks, seams, lines of mismatch running through the ice. The water froze too quickly to agree with itself. The theory says the early universe did the same thing. As it cooled through certain critical moments, different regions of space settled into slightly different states, and where those regions met, the mismatch got trapped. It could not smooth out. It froze into a line, a crack in the structure of space that has been sitting there, potentially, ever since. Now here is where it stops sounding quaint and starts to bother you. A cosmic string would be almost impossibly thin. We are not talking about something the width of a hair, or the width of a wire, or even the width of a single atom. We are talking about a defect far, far narrower than a proton, one of the particles inside the nucleus of an atom. If you tried to write its width as a fraction of a meter, you would again be walking zeros out past the decimal point, 30 of them, before you found a number. It is, for all practical purposes, a line with no thickness at all. and yet it would be heavy. This is the part that breaks the intuition. Even though the string has essentially no width, it would carry an immense amount of mass along its length, because it is a knot of trapped energy from the birth of the universe, wound impossibly tight. The numbers here defy any comfortable comparison, but let me give you one anyway, because you should not have to hold a bare figure with nothing to lean on. A single mile of cosmic string, a mile of a thing thinner than the inside of an atom, could weigh more than an entire planet. A thread you could never see, carrying the mass of a world in every short stretch of it. When you put those two facts together, thinner than a proton and heavier than a planet, you get something that does very strange things to the space around it. A cosmic string does not pull on you the way a star or a planet pulls on you, drawing you into orbit. Instead, it changes the shape of space itself in a way that is genuinely hard to picture. So let me try to make it something you can stand next to. Picture a flat sheet of paper and imagine that space near the string is like that sheet, except that a thin wedge has been cut out of it, like a single slice removed from a pie, and the two cut edges have been pulled together and joined. The sheet is still flat everywhere. There is no bump, no dimple, nothing your hand would feel as you ran it across. But a piece of the sheet is simply missing, and the space has been sewn shut over the gap. Physicists call this a deficit angle, a little wedge of reality that the string quietly deleted. It sounds like an abstraction, until you realize what it would do to the light of a distant star. If a galaxy sat far behind a cosmic string, and its light came toward you around both sides of that missing wedge, you would not see one galaxy. You would see two identical images, the same galaxy side by side, twins that are not twins, because the string in between has folded the space so that light reaches you along two paths at once. That is the cleanest fingerprint these things would leave, and astronomers have gone looking for exactly that. Pairs of matching galaxies lined up as if reflected, strung along an invisible seam. So far nothing has been confirmed, but so far is not the same as never, because the strings, if they exist, would not sit still. The theory says they whip and oscillate across the sky, and that long loops of them can pinch off and vibrate like a plucked line, except that the ends of these loops can crack like a bullwhip at very nearly the speed of light. When they crack, they should send out a burst of gravitational waves, a shudder in the fabric of space that our detectors are built to feel. This is the part that turns the cosmic string from a curiosity into a live search. The great gravitational wave observatories, the ones that listen for the ringing of colliding black holes, have also been listening for the snap of cosmic strings, and arrays of dead stars scattered across the galaxy, spinning neutron stars we use as the most precise clocks in nature, have been watched for the faint sky-wide hum that a whole population of these loops would make. Every year that passes without a detection tightens the noose a little further, tells us that if the strings are out there, they must be rarer or fainter than we feed. But tightening the noose is not the same as cutting it. Not one of these searches has been able to say the strings do not exist. They can only say, so far we have not caught one, and that leaves an uncomfortable possibility hanging in the quiet. What happens if one of these seams is not far away behind some distant galaxy, but nearer? What happens if a cosmic string, moving at nearly the speed of light, its wedge of missing space carried along with it, were to sweep through a region where matter actually lives? Behind it, the theory says, it would leave a wake, snapping material together in its path as the folded space pulled the two sides toward each other, and it would arrive with no announcement. It gives off no light in front of it to warn you. It makes no sound in the vacuum. The first thing that would tell you a cosmic string had passed would be the consequences of it having already passed. You would never see it coming. Hold on to that phrase. We're going to hear it again tonight, and by the end it is going to mean something very different than it does right now. There is a fair question hiding in all of this, and it is the one a careful listener asks. If these seams are so heavy and so strange, why has nothing ever run into one? The answer tells you how the whole search really works. A cosmic string, if it exists, would most likely be immense, not a short thread, but a line stretching across a meaningful fraction of the whole observable universe, either closed into a giant loop or running on almost without end. And there would not be many. The process that made them, if it happened at all, was thought to leave only a sparse, lonely network threaded through an enormous volume of space, so that the nearest one might be almost unthinkably far away. That is exactly why the doubled galaxy signature matters so much. You do not stumble onto a string. You catch it, if you ever do, by noticing that some object in the distant sky has an impossible twin, two images too alike to be two separate galaxies, lined up along a seam you cannot otherwise see. Astronomers have chased a handful of such candidates over the years, pairs that looked promising for a while, and every time, on closer inspection, the twin turned out to be an ordinary coincidence, two real galaxies that merely happened to resemble each other. No confirmed string has ever been found. But notice how thin the line is between not yet found and not there at all. Every candidate that dissolves under a closer look narrows the space where the strings could still be hiding, and none of it shuts the door because a sparse network threaded through a universe. This large is precisely the kind of thing that could stay hidden for a very long time. That is the quiet discomfort under this whole first step. We cannot point to a cosmic string and say, "There, that is one." But neither can we sweep the sky and say, "We have checked, and there are none." They live in the widening gap between those two sentences, allowed by the mathematics, unforbidden by the data, neither confirmed nor ruled out, exactly the kind of maybe the honest edge of physics is full of. Sit with what this first step has quietly done. We started with the one thing that felt most solid of all, the plain, smooth, empty darkness overhead. The backdrop you never think about because it seems like nothing at all. And the honest edge of physics says that backdrop may not be smooth. It may be stitched through with seams left over from the universe's first instant. Threads of folded space thinner than an atom and heavier than a world, invisible unless you happen to catch a doubled star or feel the shudder of one cracking far away. The smoothness of space, the very first thing you never think to doubt, is an assumption, a comfortable one, but an assumption all the same. That is only the fabric, though. That is only the stage everything else stands on. Before the night is over, we are going to leave the distant seams behind and come much, much closer to home. Close enough to touch the ordinary sense that we are safe where we sit. Because the next step down the countdown is not about the structure of space in the abstract. It is about something that may be moving through our own small corner of it, keeping a kind of time we're only beginning to understand, and it has a name. There may be a clock buried in the rock of this planet, and it may be set to the rhythm of a star we cannot find. That is the second thing to let go of tonight, and it is a more personal one than the first. The smoothness of space was an abstraction, something happening out among distant galaxies. This next idea comes home. It is about us, about this world, about the strange possibility that the great dyings in Earth's history, the mass extinctions that reset life again and again, might not have come at random. They might have come on a schedule, and if something keeps a schedule, then something, somewhere, is keeping the time. The story begins in 1984, with two paleontologists named David Raup and Jack Sepkoski. They had done something patient and unglamorous. They had gathered the fossil record of marine life across hundreds of millions of years, the record of which families of creatures vanished and when, and they had laid it all out to look for pattern, and they found one, or thought they did. When they plotted the extinctions across time, the peaks did not seem to fall in a scatter. They seemed to fall in a beat, roughly one every 26 million years, again and again, spaced out with a regularity that living things are not supposed to produce. Life does not usually die on a timer, but the numbers, as they read them, suggested that maybe it had. Now, a periodicity like that demands a cause, because 26 million years is far too long to be any earthly cycle. Nothing about volcanoes or oceans or shifting continents ticks that slowly and that evenly. So in the same year, 1984, several astronomers reached for the sky. Richard Muller, along with Mark Davis and Piet Hoot, proposed an answer that was as elegant as it was unsettling. What if the sun is not alone? What if our star has a companion, a second star bound to it in a long, slow, enormous orbit, a star we have simply never identified? They gave this hypothetical companion a name that told you exactly how they felt about it. They called it Nemesis, the Death Star. Here is how it was supposed to work, and it is worth walking through slowly, because the mechanism is the frightening part. Far out beyond the planets, far beyond even the most distant things we usually think of as belonging to the sun, there is a shell of frozen debris left over from the birth of the solar system. It is called the Oort cloud, and it is not a cloud you could ever see. It is a diffuse swarm of icy bodies, comets in waiting, wrapped around the entire solar system at a distance so great that light from the sun takes the better part of a year to reach its outer edge. Those comets sit out there in the cold, undisturbed, held in the faintest grip of the sun's gravity for millions of years at a time, until something stirs them, and a companion star on a long elliptical orbit would be exactly the thing to stir them. The idea was that Nemesis swings far away from the sun for most of its orbit, out to something like 1.5 light-years, which is roughly 95,000 times the distance from the Earth to the sun, a distance so large the star would be dim and easy to overlook. But then, once every 26 million years, it swings back inward, and as it passes through or near the Oort cloud, its gravity rakes across that shell of sleeping comets and flings a rain of them down into the inner solar system, a comet shower. Not one comet, but a barrage of them, arriving over hundreds of thousands of years, some fraction of which would find the Earth. And that, the theory said, is the clock. That is what could reach into the fossil record and set the beat of extinction to a stellar rhythm. Let that picture settle for a moment, because it is a genuinely strange thing to consider. It means the reason the dinosaurs are a memory, the reason whole chapters of life on this planet were closed, might trace back not to bad luck, but to a sibling of our own sun, a dark star we have never named because we have never seen it, faithfully returning on its long orbit to shake the comets loose. It would make the great extinctions not accidents, but appointments, something out in the dark keeping the clock. So astronomers went looking. If there really were a star bound to the sun, even a dim one, it should be findable. A red dwarf or a cool brown dwarf, faint invisible light, would still glow in the infrared, in the warm part of the spectrum that heat-seeking telescopes are built to see. And over the following decades we built exactly the instruments that could settle the question. The most thorough was a NASA mission called the Wide Field Infrared Survey Explorer, a telescope that scanned the entire sky in infrared light, mapping the warm objects near us with a completeness we had never had before. It found thousands of things, new brown dwarfs, cold nearby stars, drifting worlds, and it looked precisely where a companion to the sun would have to be. It found nothing. No red dwarf, no brown dwarf, no hidden star orbiting the sun at anything like the distance the theory required. The full sweep of the infrared sky came back empty of a nemesis, and so, for most scientists, the Death Star was quietly set aside. Not disproven in the sense of shown to be impossible, but ruled out in the sense that we looked as hard as we know how to look, and the thing was not there. The sun, as far as our best surveys can tell, has no companion. You might think that closes the case and lets you breathe. But here is the detail that keeps the whole thing from resting easily, the reason this belongs on a list of ideas that unsettle. The star may be gone, but the clock did not go away. Later work, looking again at the extinction record with more data, did not simply erase the pattern. One careful study found a periodicity still there, closer to 27 million years, and found it to be, if anything, more regular than before. And that regularity is itself a problem, because it is too clean. A real star on a real orbit would be jostled over the ages by the gravity of the galaxy, and the stars it passes, its timing smeared and wobbled. It could not keep a beat that precise across hundreds of millions of years, so the very sharpness that makes the pattern convincing is the same sharpness that rules out Nemesis as its cause. We may be left with a clock and no clockmaker, a rhythm in the dying of life on Earth that is real enough to measure and yet has no agreed explanation at all. That is arguably worse than a Death Star. A Death Star, at least, you could name, and if you want something you cannot set aside, something that is not hypothetical at all, the sky has already provided it. Because while Nemesis was being ruled out, our instruments were quietly tracking a real star that is genuinely coming our way. Its name is Gliese 710, and it is not a ghost. It is a small orange star sitting right now about 62 light-years away, ordinary in almost every respect except one. It is headed almost straight at us. We know this with real precision now, because a European spacecraft called Gaia has spent years measuring the positions and motions of more than 1 billion stars with an accuracy that would have seemed impossible a generation ago. And when you take Gliese 710's measured motion and run the clock forward, the tracks converge. In roughly 1.25 million years, this star is going to pass through the outer solar system, not near it, through the outer edge of it. The best current numbers put its closest approach at around 10,000 times the distance from the Earth to the Sun, which sounds enormous until you remember that this is exactly the neighbourhood where the Oort cloud lives. Gliese 710 is going to drive straight into our shell of sleeping comets. The astronomers who worked out its path did not soften their language. They called it the strongest disrupting encounter in the entire future, and recorded history of the solar system. When it passes, its gravity is expected to stir the Oort cloud far more forcefully than any known star has in ages, loosening a shower of comets that could drift inward for millions of years afterward. Some estimates suggest the inner solar system could see something like 10 comets, bright enough to catch with the naked eye every year, for 3 or 4 million years running. A sky periodically streaked with visitors, all of them shaken loose by a single passing star. The planets themselves would be safe. Gliese 710 will not move the Earth or nudge its orbit, but it will reach into the cold outer dark, exactly as Nemesis was imagined to, and it will do it for real. It helps to understand why a passing star is so good at loosening comets, because the mechanism is gentler and stranger than a collision. The comets of the Oort cloud are held to the Sun by a grip so faint that it barely qualifies as a grip at all. Out there, a comet may take millions of years to complete a single slow orbit, drifting at the very limit of what the Sun can hold. A body held that loosely does not need to be struck to be dislodged. It only needs to be tugged, slightly, at the right moment, and a star drifting through changes the balance just enough that some of those comets slip their leash and begin the long fall inward. This is why a star does not have to hit anything to be dangerous. It has to pass close, and pass slowly, and its gravity does the rest over the following hundreds of thousands of years. And here is the part that should recalibrate your sense of how safe the neighbourhood really is. Stars pass by the Sun far more often than most people imagine. Over millions of years, encounters at the scale of a light year or two are not rare accidents, but a steady drumbeat, the ordinary traffic of a galaxy in which everything is in motion, in which the Sun and all its neighbours are sweeping around the centre on their own long orbits and drifting past one another as they go. Gliese 710 is simply the closest approach we can currently see coming, the standout in a long, quiet procession. The solar system is not a sealed room after all. It is a clearing in a moving forest, and the trees drift past on their own schedules, occasionally close, and every so often close enough to shake something loose. So notice what this second step has taken from you. We started this part with the quiet assumption that we are safe where we sit, that our little solar system is a stable, closed room, that the extinctions in our past were random misfortune and nothing keeps time with them, and the honest reading of the evidence leaves all of that in doubt. There may be a rhythm in the great dyings that no one can explain. There may not be a Death Star, but there is a real star on its way, and the comets that would come are the same kind of thing as the cosmic string from a moment ago, a threat that carries no warning ahead of it, that you would only know by its arrival. You would never see it coming. There is that phrase again. But a comet, at least, is something you could eventually see, a light in the sky with a name. The next step down removes even that small comfort, because the next thing we're going to talk about may already be here, drifting in our own solar system, closer than the passing star and far, far harder to find. In fact, it may be a thing that by its very nature gives off no light at all. There might be a black hole in our solar system, not far away, not in some other system, not a thing we watch through a telescope at a safe remove. Here, in the family of the Sun, and if it is here, it is the size of a piece of fruit. That is the third assumption we're going to set down, and it is the assumption that we would notice something that big and that dangerous if it were close to us. Surely, you think, a black hole in our own solar system is the kind of thing we could not possibly miss. Tonight we're going to see why that comfortable thought does not hold, and the reason it does not hold is the most quietly frightening thing about the whole idea. To get there, we have to start with a real, ongoing mystery, one that has nothing fringe about it at all. Out beyond Neptune, in the cold and slow-moving reaches of the solar system, there is a population of small, icy worlds we call trans-Neptunian objects. They are leftover pieces from the making of the planets, drifting on enormous orbits that take thousands of years to complete. And for a while now, astronomers have noticed something odd about a handful of the most distant ones. Their orbits are tilted and turned in a way that does not look random. They seem to lean together, to cluster, as if some unseen gravity has been quietly herding them into alignment over long stretches of time. The most popular explanation for this clustering is called Planet 9. The idea is that there is a genuine ninth planet out there, something like 5 to 10 times the mass of the Earth, orbiting hundreds of times farther from the Sun than we do, too dark and too distant for us to have spotted yet, but massive enough that its pull, acting over millions of years, gathers those far-flung icy worlds into the pattern we see. It is a perfectly respectable hypothesis, and there are people searching for that planet right now, sweeping the outer sky for a faint moving point of light. But in 2019, two physicists named Jakob Schultz and James Unwin asked a question that turns the whole search on its head. They agreed that something out there is doing the herding. They agreed it has about the mass of 5 Earths. But they pointed out that we have been assuming, without quite noticing we were assuming it, that this something is a planet. And gravity does not care what an object is made of. Gravity only cares how much mass is there and where. So they asked, in the title of their paper, a question that sounds like a provocation and is in fact a serious piece of physics. What if Planet 9 is not a planet at all? What if it is a primordial black hole? To feel the weight of that, you have to understand what a black hole of that mass would actually be like, because it does not match the picture in your head. When we talk about black holes, we usually mean the corpses of giant stars, objects several times the mass of the Sun and more, with a reach that would swallow a city or a world. But the size of a black hole scales with its mass, and 5 Earth masses is, on the scale of black holes, almost nothing. If you took 5 Earths worth of mass and packed it down until it became a black hole, the resulting object, the region from which nothing can escape, would be about 5 centimeters across. 5 centimeters. You could cup it in your hands if cupping it in your hands did not mean the end of your hands and everything attached to them. It would be, in size, a grapefruit with the mass of 5 worlds, drifting somewhere in the dark past Neptune. Now, where would such a thing come from? Not from a dying star. A star cannot make a black hole that small. Instead, the theory reaches back to the very beginning of the universe, to that same first fraction of a second we keep returning to tonight, when the cosmos was so dense and so violently uneven that some regions may have collapsed directly into black holes on the spot. These are called primordial black holes born not from stars but from the raw lumpiness of the newborn universe, and they could in principle come in almost any size, including small. They have been proposed for decades as a candidate for dark matter, the invisible mass that seems to outweigh everything we can see. And Schultz and Unwin noticed something suggestive. There was a separate, unexplained hint in the data, an excess of brief brightening events in a long survey of stars, the kind of flash you get when a dark, compact object drifts in front of a distant star and its gravity focuses the light toward you for a moment. That excess pointed to a population of small, dark, planet-mass things wandering the galaxy. And if such things exist, then the solar system could have captured one, long ago, and it could be out there now, doing exactly the herding we attribute to Planet 9. Here is the part that should raise the hair on your arms. If Planet 9 is a planet, we will eventually find it, because a planet, however dark and distant, still catches a little sunlight and shines with a faint reflected glow that a patient telescope can pick out. But a black hole reflects nothing. It emits nothing you could point a normal telescope at. A 5-centimeter black hole in the outer solar system would be, for all ordinary purposes, perfectly invisible. It could be out there right now, tugging on the icy worlds, and no survey of reflected light would ever reveal it, because there is no light to reflect. We could look straight at the patch of sky it occupies and see only stars behind it. So how would you ever catch such a thing? Schultz and Unwin had an answer, and it is a strange and clever one. If the black hole formed in the early universe, it might be wrapped in a halo of dark matter, drawn in around it by its gravity. And in some theories, dark matter particles, when they crowd together densely enough, annihilate one another and release a puff of high-energy light, gamma rays. So the way to find a black hole in our own solar system would not be to look for the black hole. It would be to look for the faint glow of dark matter, destroying itself in the space just outside it. You would hunt for a small, still point of gamma-ray light out beyond the planets, hanging in the dark where nothing should be shining, and that glow, if you found it, would be the signature of a black hole the size of a grapefruit that had been keeping us company all along. You might reasonably object that capturing a passing black hole sounds far too lucky to take seriously, and Schultz and Unwin met that objection head-on. They admitted that the odds of the solar system capturing a wandering planet-mass black hole are indeed very small, but then they asked the question that makes the idea click into place. How much less likely is that than the alternative? Because the ordinary Planet 9 idea also requires catching something. If Planet 9 is a free-floating planet, a world drifting alone through the galaxy that the Sun happened to snag into orbit, then that too is an unlikely capture of a rare object. And when you work the numbers, capturing a primordial black hole of a given mass turns out to be no more improbable than capturing a free-floating planet of the same mass. Neither is likely. But neither is more of a stretch than the other. So if you're already willing to entertain that the Sun caught a rogue planet to explain the orbits at its edge, then honesty requires you to admit it could just as easily have caught a rogue black hole, because gravity cannot tell the difference, and neither, from a distance, can we. What tipped the two physicists toward taking it seriously was that second clue, the one from the survey of brightening stars. For years, a long-running project had been watching millions of stars for the tiny temporary flares that happen when a dark, massive object drifts between us and a background star, and its gravity briefly focuses the starlight, an effect Einstein predicted and we call microlensing. That survey had turned up more of these brief flares than expected, an excess that hinted at a hidden population of dark, compact, planet-mass objects wandering the galaxy, more of them than the known count of rogue planets could comfortably explain. Primordial black holes would fit that excess, and if the galaxy is quietly full of them, drifting between the stars in numbers we're only beginning to suspect, then the idea that one of them settled into the outer solar system long ago stops sounding like a wild coincidence and starts sounding like a possibility we have simply never looked for in the right way. It also connects to the largest missing piece in all of cosmology. Most of the matter in the universe is invisible, detectable only by its gravity, and we still do not know what it is made of. Primordial black holes are one of the candidates for that dark matter, and if they make up even a fraction of it, then the space around us is threaded with dark, compact, ancient objects, and the one supposedly tugging on our own solar system's edge would simply be the nearest example of something the whole cosmos is quietly full of. Take a slow breath here, because this one earns it. We began this part with the confident sense that we would surely notice anything so extreme so close to home. And what the physics shows us is that the most extreme object we know of, a black hole, could be sitting inside our own solar system, could be the very thing subtly rearranging the orbits at the edge of the Sun's domain, and it could do so in total silence, giving off no light, announcing itself only, if at all, by the ghostly gamma glow of invisible matter unmaking itself nearby. We would not see it coming, we would not see it at all, we would only perhaps see the faint shine of the dark falling in. And I want you to notice the shape the countdown is taking, because it matters for where we are going. The first step questioned the smoothness of space far away. The second brought a threat into our own neighbourhood, but kept it as something that would, eventually, be a light in the sky. This third step has taken that away. Now the danger is not only near, it is by its nature unseeable, a thing defined by the fact that it lets nothing out. Each step has been quietly moving the fear closer to us, and harder to look at directly. But so far, every one of these things, however hidden, has still been an object. A string, a star, a black hole. Something out there, in some real location, that you could in principle travel to and stand beside. The next step down the countdown leaves that behind entirely. Because the next idea is not about any single object at all. It is about the fate of every object, everywhere, given enough time. It is about what happens to matter itself, to the atoms in the ground and the atoms in your hand, when you let the clock run not for billions of years, but for a length of time so long that billions of years round down to nothing. And what happens to matter, in the end, is that it forgets how to be anything but iron. Nothing is permanent. You know that already, in the ordinary way. People are not permanent, buildings are not permanent, mountains wear down and coastlines move. But underneath all of that impermanence you carry a quiet assumption that the material itself endures. The stone crumbles, but the atoms in the stone go on. The body fails, but the atoms it was made of scatter and continue, unchanged, ready to be something else. Matter, you assume, is forever. The forms come and go, but the stuff is eternal. That is the fourth thing we're going to set down tonight, and to do it we have to leave the present entirely. We have to walk forward in time so far that the distances stop meaning anything, into a future compared to which the entire history of the universe up to this moment is not even a first breath. And our guide for this walk is a physicist named Freeman Dyson, who in 1979 wrote a paper with a title that already sounds like a meditation. He called it Time Without End. In it, he did something almost no one had bothered to do. He asked, seriously, and with the full machinery of physics, what happens to everything if you simply let the clock keep running? Not for billions of years, forever. To follow him, you first have to understand where matter would like to settle if it could. Every atom heavier than a certain point, every atom of gold, of lead, of uranium, is carrying a kind of surplus. Its nucleus is packed more loosely than it would prefer, and given the chance, it would rather break down into something more tightly bound and release a little energy in the process. And every atom lighter than that point, every atom of hydrogen, of helium, of the carbon and oxygen you're partly made of, is carrying the opposite kind of surplus. It would rather fuse together into something heavier and more tightly held and release a little energy that way. There is one place where these two tendencies meet and cancel, one element that is more settled, more tightly bound, more at rest than any other. That element is iron. Iron is where matter wants to go. Iron is the bottom of the valley, the place everything is trying ever so slightly to roll down toward. The reason the universe is not already made of iron is that rolling down that hill is monstrously hard. To fuse light atoms together, or to break heavy ones apart, normally takes furnace conditions, the crushing heat and pressure at the heart of a star or the fury of an exploding one. In the cold of ordinary space, atoms simply do not have the energy to make the change. A lump of rock will sit as rock, a bar of gold will sit as gold, seemingly forever, because the path to iron is blocked by a wall it cannot climb. And here is where Dyson reached for the strangest tool in physics, a tool we usually only meet in the world of the very small. Quantum mechanics says that a particle facing a wall it cannot climb has, nonetheless, a tiny, tiny probability of simply appearing on the other side of it, of tunneling straight through the barrier as if it were not there. That probability is absurdly small. For any given atom, on any given day or year or million years, it essentially never happens. But essentially never is not the same as never, and Dyson was not working with days or millions of years, he was working with forever. Given enough time, he showed, the impossible becomes routine. Over long enough stretches, atoms will tunnel through the barrier that blocks them from iron. Slowly, unimaginably slowly, the gold will decay toward iron, the rock will fuse toward iron, everything solid and cold in the universe will creep, one improbable quantum tunneling event at a time, toward that single, most settled element. Dyson put a number on how long this takes, and the number is one of those figures that the mind cannot hold, so I will hand it to you gently. Write down a 1, and then write 1,500 zeros after it. That many years, that is roughly how long it takes for ordinary matter to finish its slow collapse into iron. A planet, a dead star, a wandering rock, all of it, over a 1 followed by 1,500 zeros of years, becomes a sphere of solid iron. An iron star, cold and dark, sitting where a world or a stellar corpse used to be. Let me take you there, because a number like that means nothing until you stand inside it. Imagine you're standing on the surface of a world an unthinkable distance into the future. The sky above you is perfectly black and it is empty. There are no stars because the last star burned out so long ago that its death is not even recent history in this place. It is buried under further oceans of time. There is no warmth. The temperature here is a hair above the coldest anything can be, and it has been that cold for longer than you have words for. The ground beneath your feet was once rock, ordinary rock, the crust of some quiet planet. But it is not rock anymore. Atom by atom, over a span of years you would have to write as a 1 trailing 1,500 zeros, it has been turning into iron. It is turning still. Somewhere under your feet, right now, a single atom is tunneling through a wall it should not be able to cross, and settling 1 step closer to iron, and releasing a whisper of energy so faint that nothing could measure it. Nothing moves fast enough here for you to see any of it. There is no wind, no sound, no light, no event, and yet the whole world is in motion. The slowest motion there is, every atom of it drifting down toward the same final metal. You're standing on a corpse that is still, patiently, becoming iron. That is the age of iron, and it is where all solid things are going. And here is the part that Dyson followed even further, the part that closes even this door. You might think an iron star, cold and settled at the very bottom of the valley, would at last be the end, the final resting state, matter having reached the one form it can never leave. But it is not the end, because that same quantum tunneling that turned the world to iron does not stop once iron is reached. Given time beyond even the time we just described, an iron star can tunnel again, this time collapsing its own structure, its atoms creeping toward the impossible density of a neutron star, or, further still, folding all the way down into a black hole. The timescales for this make the previous ones look immediate. If the age of iron arrives after a 1 with 1500 zeros, the collapse of iron stars into black holes arrives after a number so large you cannot even write it in the ordinary way. You have to write it as a 1, followed by 10, raised to a further power of 76, a tower of exponents, a length of time that the phrase length of time can barely survive. But the direction is what matters, not the digits. The direction is relentless, and it is one way. Follow the clock far enough, and the planets are gone, not scattered but transformed. The dead stars are gone. Even the iron is gone. Matter does not endure in any form you would recognize. It creeps downhill, forever, through walls it should not be able to cross, towards states of ever greater density and ever greater stillness, until there is nothing left that could be called an object at all. I want to give you a way to hold that first number, the one followed by 1500 zeros, because a figure like that can wash over you and leave nothing behind unless you slow it down. Start with the age of the universe so far, roughly 14 billion years. Written out, that is a 14 followed by 9 zeros. It already feels like more time than the mind can carry. Now compare it to the age of iron, a 1 followed by 1500 zeros. The gap between those two numbers is not a matter of one being somewhat longer, or vastly longer, or even incomprehensibly longer. It is that the entire history of the universe up to now, every star that has ever burned, every galaxy that has ever formed, all of it occupies the first 14 billion years, which against 1500 zeros is not the opening chapter, not the opening sentence, not even the first letter of the first word. It rounds, exactly and completely, to 0. If you stood at the moment iron finally claims the last cold world and looked back, the entire era of stars and life and light would not appear as a distant beginning. It would be indistinguishable from the very first instant, crushed against the origin by the sheer weight of the time that came after. We do not live near the beginning of the universe. We live at the beginning, so close to the start that everything that has ever happened is still, on the true scale of things, the opening flicker. And that is why matter feels permanent to us. Not because it is, but because we are looking at it during the one brief moment when the great transformation has not visibly begun. It is worth pausing on why iron, of all things, is the destination, because it is not arbitrary. Every atomic nucleus is a balance between forces that want to hold it together and forces that want to push it apart, and the quality of that balance, how tightly the nucleus is bound, changes from element to element. If you chart it, the binding rises to a single peak and then falls away, and iron sits almost exactly at the top of that peak, the most tightly bound, the most settled, the least willing to become anything else. Everything heavier is carrying tension it would rather release by breaking down toward iron. Everything lighter is carrying tension it would rather release by building up toward iron. Iron is simply where all the roads lead, the one arrangement of matter that has nothing left to give up, the floor of the valley every other element is, given time enough, slowly rolling toward. So sit with what this fourth step has quietly removed. We began with the assumption that runs underneath all the others, the belief that even as forms decay, the substance goes on, that matter is the one permanent thing. And the honest extrapolation of known physics says no. Matter is not permanent. It only looks permanent because we live in the tiniest sliver at the very beginning of time, a sliver so early that the great transformation has not visibly started. The atoms in your hand feel eternal to you, the way the smoothness of space felt eternal, the way your safety in the solar system felt eternal. It is another of the things you never think to doubt, and it is another assumption, true only for now, true only because now is so absurdly early that the universe has not yet had time to show you otherwise. There is something else hidden in that thought, and it is going to open the door to the next step down. We keep saying given enough time, and treating enough time as if it simply supplies more of the same, more years, more decay, more slow change in one direction. But time, in enormous quantities, does something stranger than merely continuing. If a system is closed and bounded, and you give it not just a great deal of time but an endless supply of it, it stops only moving forward into new states. It begins, eventually, to come back around. The next idea on our countdown takes the forever we have been playing with and asks what it really implies. And the answer is that in a universe with endless time, nothing that can happen happens only once. Not the arrangement of atoms in an iron star, not the arrangement of atoms in this room, not the arrangement of atoms that is you. Let us stop for a moment, halfway down, and put the pieces together, because we have quietly taken quite a lot apart. We began with the smoothness of space, and found it might be stitched with invisible seams. We looked at our own safety in the solar system, and found a rhythm in extinction no one can explain, and a real star already on its way toward our comets. We looked at the idea that we would notice a great danger nearby, and found that a black hole the size of a grapefruit could be drifting past Neptune, giving off no light at all. And we looked at the permanence of matter, the deepest flaw of all, and found that even the atoms are slowly, over spans beyond imagining, creeping toward iron and then toward nothing. 4 assumptions, 4 of the things you never think to doubt, and each one, on close inspection, turned out to be a comfortable belief rather than a guarantee. Notice that the fear has been moving. It started far away and abstract among distant galaxies. Then it came into our neighbourhood. Then it came unseeably close. Then it stopped being about any place at all and became about the fate of all matter everywhere. Each step has drawn the horror inward, closer to us, harder to hold at arm's length. And now, at the midpoint, it is going to take one more step in that direction, and it is going to reach something you have been assuming so quietly that you may not have noticed you were assuming it. Not the permanence of matter, the uniqueness of you, the simple, unspoken certainty that this moment, this exact you, thinking this exact thought, is happening only once. The idea that undoes this comes not from cosmology at first, but from ordinary physics, from a proof written by the French mathematician Henri Poincaré in 1890. It is called the recurrence theorem, and on its surface it sounds harmless, almost dull. It says this: take any physical system that is closed, meaning nothing leaks in or out, and bounded, meaning it has only so much room and so much energy to work with. Let it evolve. Let it shuffle through its possible arrangements however it likes. Poincaré proved that if you wait long enough, the system must return to a state arbitrarily close to the one it started in. Not approximately, as close as you care to specify. And having returned once, it must return again, and again, infinitely many times. A closed, bounded system cannot wander forever through new configurations. Sooner or later, it comes home, and then it does it once more, forever. For a small system, you can almost picture this. Imagine a sealed box with a handful of gas molecules bouncing around inside. Right now, they are all crowded in one corner. Let them go and they spread out, filling the box evenly, and you would swear they will never all gather back into that one corner again. But Poincaré proved that they will. If you wait long enough, the random bouncing will, by pure chance, bring every last molecule back into that corner, recreating the starting arrangement exactly. It might take a length of time that dwarfs the age of the universe, but in a closed, bounded box it is not merely possible, it is guaranteed, and it will happen not once, but endlessly. Now take that harmless little theorem and point it at the cosmos. If the universe, or some bounded region of it, is a closed system with a finite amount of room and energy, then it is exactly the kind of system Poincaré was describing, just enormously larger and slower, which means that every arrangement of matter it is capable of producing, it must eventually produce again. Every configuration recurs, and when you say every configuration, you have to be honest about what that includes. It includes the arrangement of gas and dust that made this galaxy. It includes the arrangement of atoms that made this planet, this room, this night. It includes the precise arrangement of matter that is your body and your brain in the act of having this precise thought. All of it, given enough time, must come back. Not as a copy somewhere else, as a return of this, again, and then again, without end. How long would you wait for a recurrence on that scale? The physicist Don Page once worked out an estimate for a universe like the kind ours may become, and the number he arrived at is one of the most extraordinary figures ever written down in a serious paper. It is so large that you cannot express it as a 1 with some zeros after it. You have to build it as a tower. 10 raised to a power, and that power is itself 10 raised to a power, and that power is itself 10 raised to a power. A number stacked 3 and 4 levels high. It is so enormous that it hardly matters whether you measure it in seconds or in years, or in the entire current age of the universe, because those units differ by mere handfuls of zeros, and this number laughs at handfuls of zeros. It is, for all human purposes, simply the length of forever. But it is finite, and finite is the only thing the theorem needs. I want to slow all the way down here, because this is one of the places tonight where an abstract theorem turns into something you feel in your chest. We do not usually fear repetition. If someone told you that in some incomprehensible future the same swirl of gas would happen to form again, you would file it under harmless coincidence. But make it personal and it changes. The recurrence theorem does not promise that something like this will happen again. It promises that this will happen again. You, lying here, in the quiet, hearing these words, having whatever small private thought you're having underneath them, that exact state of your atoms is a configuration the universe is capable of, and in a closed and eternal cosmos, every configuration it is capable of, it must return to, infinitely often. So this moment is not a one-time event. It is a station the universe passes through, has passed through before across unthinkable gulfs of time, and will pass through again and again forever. And here is the blade of it. Each time it returns, it is new. There is no memory carried across the gap. The you of the last recurrence did not remember the one before, and the you of the next one will not remember this. Every single return is lived as the first and only time. You're not being given eternal life. You're being given this one moment, this exact moment, on an endless loop, with the loop erased at every turn so that you can never know you are inside it. Not a continuation, a repetition, felt fresh, forever. That is the loss the eternal return asks you to hold. Not the loss of your life, but the loss of its uniqueness, and the loss of any escape from it, at the same time. The philosophers reached for this idea long ago as a metaphor, a thought experiment about how you might live if you had to live it all again. Poincaré, without meaning to, may have turned the metaphor into physics. I should be honest with you, as this channel always tries to be, about where the certainty runs out. The recurrence theorem is airtight, but it only bites if the universe really is closed and bounded and eternal, and that is exactly what we do not know. If instead the universe keeps expanding forever, thinning and cooling toward the kind of endless dilution we touched on with the iron stars, then it may never be a bounded system at all, and the returns may never come. The eternal recurrence may be a horror that the shape of our particular universe spares us from, or it may not. We genuinely do not know which universe we live in, the one that comes home or the one that never does. And that uncertainty is its own strange thing to lie under in the dark, not knowing whether this moment is unrepeatable, or whether it is one turn of a wheel with no beginning and no end. There is an older version of this idea, and it is worth setting beside the physics, because the two illuminate each other. Long before Poincaré, the philosopher Friedrich Nietzsche posed the eternal return as a thought experiment about how you might live. Imagine, he said, that a voice told you in your loneliest hour that you would live this life again and again, endlessly, every pain and every joy and every small dull moment repeated exactly, forever. Would that knowledge crush you, or could you find a way to live so that you could welcome it? For Nietzsche it was a test of the spirit, a way of asking whether you could love your life enough to want the whole of it back unchanged. What Poincaré added, without meaning to, was the possibility that this is not a test but a description, that the recurrence is not a hypothetical a philosopher invents to measure your courage, but a straight consequence of physics in a closed and eternal world. And when it becomes physics, the one comfort Nietzsche left open quietly closes, because his version, however heavy, at least allowed for a kind of acceptance, a yes said to the whole of your life. The physical version does not even grant you that, because it takes the memory away. There is no accumulated wisdom carried from one turn of the wheel to the next, no sense in which you get better at it, no chance to say yes the second time having learned from the first. Each return is sealed off from all the others, lived blind as though it were the only one. You cannot brace for it, because you do not know it is coming. You cannot savour it as a return because it does not feel like one. You cannot even take grim comfort in the repetition, because the repetition is invisible from the inside. The universe would be spelling out your exact moment over and over across gulfs of time that have no name, and every single instance would experience itself as first and final and alone. And the number that governs all of this, the recurrence time, deserves one more moment of respect, because it does something almost paradoxical. It is finite. That is the whole engine of the horror. If it were truly infinite, the returns would never come, and you would be safe in your uniqueness. It is precisely because the number, however monstrous, is a finite number, a definite quantity you could in principle write down given enough paper and enough patience, that the theorem bites. Finiteness is usually the thing that reassures us, the sign that something has an edge and an end. Here it is the opposite. Here it is the finiteness of the weight that guarantees the return. Either way, look at what the midpoint has done. We have crossed from fears about the world to a fear about the self. The first half of this countdown asked whether the things around you are what they seem. The second half, which begins now, asks whether you are what you seem, whether your moment, your memory, your experience, your very ending are what you assume them to be. And the next step down turns from the far future to the distant past, and to a discovery that is almost unbearably poignant. Because it turns out the universe is not only capable of repeating its history, it is also, right now, quietly erasing it. There is a chapter of the cosmic story that is being deleted as we speak, and we happen to be alive in the last age when it can still be read. The universe is erasing the evidence of its own birth, slowly, quietly, and completely. And the strangest part is that we happen to be alive during the brief window when the erasing is not yet finished, when the truth can still be read. Future minds, born too late, will look out at a cosmos that has hidden its own history from them, and they will get the story wrong, and there will be nothing in their sky to tell them so. That is the fifth assumption we set down tonight, and it is a subtle one, because it is not an assumption about the world so much as an assumption about knowledge. We take for granted that the truth, once discovered, stays available, that the great facts about the universe, the ones we worked so hard to uncover, are simply out there to be found by anyone who looks carefully enough, now or in a billion years. We assume the evidence is permanent. That is the thing you never think to doubt this time. And it turns out the evidence has an expiration date. The physicists who spelled this out most clearly were Lawrence Krauss and Robert Scherer, in an essay from 2007 with a title that already carries a chill once you understand it. They called it The Return of a Static Universe and the End of Cosmology. To feel what they meant, you have to remember how we know what we know about the cosmos, and the whole story rests on one discovery. About a century ago, we learned that the universe is expanding, that the distant galaxies are all rushing away from us, and that the farther away a galaxy is, the faster it flees. That single fact is the foundation of modern cosmology. It is how we know there was a beginning. Run the expansion backward in your mind, and everything crowds together, hotter and denser, until you arrive at the fiery origin we call the Big Bang. The expanding galaxies are the evidence. They are the visible proof that the universe has a history and a birth. There is a second great piece of evidence too, just as important. The heat of that original fireball is still around us, cooled now to a faint whisper of microwave radiation that fills all of space, arriving from every direction at once. We call it the cosmic microwave background, and it is, in a real sense, the afterglow of creation, the oldest light there is. When we want to study the newborn universe, we read that light. Between the fleeing galaxies and the ancient afterglow, the cosmos hands us freely the two clearest pieces of testimony about where it came from. We did not have to be clever to find them, we only had to look. And now here is what Krauss and Scherer pointed out. Both of those pieces of evidence are temporary, because the expansion of the universe is not holding steady. It is accelerating, driven by the mysterious pressure we call dark energy, and as it accelerates, the distant galaxies are not just moving away, they are moving away faster and faster, and the space between us and them is stretching more and more quickly. Follow that forward in time, and there comes a point for each distant galaxy where the space between us is stretching faster than its light can cross the gap. When that happens, the galaxy does not just grow dim, it leaves. Its light can no longer reach us at all. It passes beyond what we call the cosmic horizon, the edge of what can ever be seen, and from our point of view it is simply gone, as surely as if it had never been. Now widen that out. Our galaxy is bound by gravity to a small collection of nearby galaxies, our local group, and gravity holds that little cluster together against the expansion. In time, these will merge into a single large galaxy. But every other galaxy in the universe, the hundreds of billions of them beyond our gravitational island, is on the far side of the accelerating stretch. One by one, over the coming tens and hundreds of billions of years, they will each cross that horizon and disappear from view. And the afterglow of creation, that faint microwave whisper, will stretch along with the expanding space until its wavelengths grow so long and so faint that no instrument could ever register them. It too will fade past the edge of the detectable. So picture an astronomer 100 billion years from now or more standing on some world in that final merged galaxy, doing exactly what we do. Looking up, building instruments, asking honest questions about the cosmos. What do they see? They see their own galaxy, an island of stars, and beyond it in every direction perfect, empty, changeless black. No fleeing galaxies, because the fleeing galaxies have all crossed the horizon and vanished. No afterglow, because the afterglow has stretched itself into undetectable silence. Nothing in their sky moves or recedes. Nothing testifies to a beginning. As far as their best telescopes can tell, they live in a single galaxy floating in an eternal static void, and that is all there has ever been or will ever be. And they will be wrong. Completely, tragically wrong, through no fault of their own. They will do good science. They will measure carefully and reason soundly, and they will conclude that the universe is static and eternal, because every shred of evidence that could have told them otherwise has already left the observable sky. The expansion, the beginning, the afterglow, the dark energy driving it all, none of it will be visible. Their honest, careful cosmology will describe a universe that does not exist, and nothing available to them could reveal the mistake. The truth will not be hard for them to find. It will be impossible, because the universe will have deleted it. Here is the line I want you to carry out of this part, the one we are going to return to before the night is done. We are alive in the last chapter that can still be read. Right now, in this era, the evidence is still in the sky. The galaxies are still fleeing where we can see them. The afterglow is still arriving. The book of the universe's origin is still open, and we happen to have shown up while its pages are legible. Give it enough time and that book closes, not because anyone shut it, but because the universe carries its own pages away past the horizon, one by one, until the story cannot be reconstructed. We are not the last people who will look up, but we may be among the last who can look up and see what actually happened. And I have to tell you the thought that makes this genuinely vertiginous, rather than merely sad. It is not only about the far future. If the universe deletes evidence over time, then some evidence has already been deleted. Some galaxies have already crossed beyond our horizon, in the billions of years before we arrived, and we will never know they were there. There may be whole features of the true cosmos, real chapters of the real story, that were already carried off before humanity ever opened its eyes, and we are reconstructing the universe from a book that is already missing its opening pages. We flatter ourselves that we see the whole picture. We may be seeing only what has not yet been erased. Our confidence that we understand the cosmos may itself be a product of the particular, privileged, temporary moment we happen to occupy, when a certain amount of the evidence still remains. It is worth being concrete about how far off this is, and also about why the distance does not make it any less unsettling. The full erasure Krauss and Scherer describe unfolds over tens and hundreds of billions of years, a future so remote that the sun will be long dead and the earth long gone before it arrives. So this is not a threat in any ordinary sense. No one you will ever know is in danger from it, and yet the reason it belongs here, the reason it genuinely disturbs the people who study it, is that it attacks something we thought was safe from time altogether. We're used to the idea that things decay, that stars die, and worlds end. We're not used to the idea that knowledge decays, that a true fact about the universe, once available, can become permanently and irretrievably unavailable, not because anyone forgot it, but because the universe physically removed the evidence from view. Truth, we assumed, is the one thing that does not expire, and that assumption is what this quietly dismantles. Consider what it means told from the other side, from the point of view of those far future astronomers. They will not be foolish, and they will not be lazy. They will build instruments as fine as ours or finer, and they will reason as carefully, and they will look out at a single island of stars in a changeless dark and conclude, correctly given everything they can possibly see, that this is all there is and all there ever was. Their error will be invisible to them, and it will be undetectable, because the very evidence that could correct it will have left their universe forever. There is no experiment they could run, no cleverness they could apply, that would recover the missing truth, because the truth will be on the far side of a horizon that nothing can cross. And now turn that around to face us, which is the part that should make you sit up in the dark. If the universe removes evidence as time goes on, then evidence has already been removed. In the billions of years before we arrived, galaxies that were once visible have already slipped beyond our horizon, carrying whatever they could have told us with them. There may be features of the true cosmos, real and important ones, that were already gone before the first human ever looked up. We are not the future astronomers, comforted and wrong, but we may be their ancestors along the same road, already missing the opening pages of the book, already reconstructing the story from a text with its beginning torn away, and flattering ourselves that we hold the whole of it. So the fifth step takes away the permanence of knowledge itself, not one of the things around you, but your trust that the truth stays findable. And it leaves us in a strange and tender position. We're not at the centre of the universe. We're not at the most important time. But we may be at the most legible time, the age when the most of the story is still visible, and that is a kind of accident worth being quiet about. There is a thread from this that leads straight to the next step, and it is worth pulling. We have been talking about looking outward, past the galaxies, toward the edge of what can be seen, and about how that edge, that horizon, hides things from us. We have been treating the horizon as the boundary of our knowledge. But the next idea asks a far more disturbing question about that boundary. What if the horizon is not just the edge of what we can see? What if it is the edge of what there is, in the way the surface of a black hole is an edge that only lets things in? What if everything we call the universe, all of it, every galaxy inside our horizon, is itself the inside of something? What if there is no outside to reach at all because we are already within? Everything you have ever seen, every star, every galaxy, all the light that has ever reached your eyes may be sealed inside a single black hole, not heading toward one, not orbiting one, inside one, right now and always. The universe you think of as the outermost thing there is may itself be an interior, with a wall around it that only ever lets things in. That is the sixth assumption we are setting down, and it is the one that removes the very idea of an outside. All night we have talked about things at the edge, beyond the horizon, out past the farthest galaxies, and we have quietly assumed that out there somewhere is the exterior of everything, the true open beyond. This next idea says there may be no such place, that the beyond is a wall and we are within it, and there is no version of the story where you climb over the top and look down at the universe from without. It is the thing you never think to doubt precisely because it seems too basic to state. Of course there is an outside, there is always an outside, except, perhaps, here. The idea is called black hole cosmology, and it is a minority view, but it is not a fringe one in the dismissive sense. It has been developed by serious physicists over decades, tracing back to work in the early 1970s and carried forward in detail by a theoretical physicist named Nikodem Popławski. To understand what he is proposing, you have to first let go of the cartoon of a black hole as a bottomless drain that crushes everything to a point. That cartoon comes from taking our equations at face value all the way down to the centre, where they predict a singularity, a place of infinite density where physics itself stops making sense. Most physicists suspect the singularity is not real, that it is a sign our theory breaks down and something else must take over. Popławski's work is one attempt to say what that something else is. He builds on a richer version of Einstein's theory of gravity, one that includes a property of matter we usually ignore, the intrinsic spin of the particles it is made of. In this fuller picture, when matter collapses inside a black hole, the spin of all those particles produces a kind of twisting in the fabric of space-time, a resistance that grows stronger and stronger as things are squeezed tighter, and at a critical density, before a singularity can form, that twisting wins, the collapse halts, and then it reverses. Instead of crushing down to an infinite point, the matter rebounds, and it begins to expand. It bounces. Now sit with what that bounce would look like from the inside. You have matter that was collapsing that suddenly reverses and starts expanding rapidly, growing, unfolding into a new region of space that was not there before. Does that sound familiar? It should. Because that is exactly what we say happened at the beginning of our own universe. A sudden onset of expansion from an incredibly dense hot state, space itself unfolding and growing. Popławski's proposal is that these are the same events seen from two sides. What looks, from the parent universe, like matter falling into a black hole and collapsing looks, from the inside like a big bang, the birth of a whole new universe expanding on the far side of the horizon. And if that is true, then every black hole that forms in our universe may be giving birth to a baby universe of its own, sealed off behind its horizon, forever inaccessible to us. And our universe, the one we live in, the one we are so sure is the outermost thing, may itself be the inside of a black hole that formed in some larger universe we can never see. There is a coincidence that has nagged at physicists for a long time, and that this idea explains almost too neatly. Every mass has associated with it a particular size, the size it would have to be squeezed to in order to become a black hole. For the Sun, that size is a few kilometers. For the Earth, it is smaller than a marble. Now take all the mass in the observable universe, everything we can see, and ask how big a black hole that much mass would make. When you run that calculation, you get a size that comes out remarkably close to the actual size of the observable universe itself. In other words, the universe has just about exactly the mass and size it would need to have if it were the interior of a black hole. That might be a meaningless coincidence, or it might be the most important clue we have been walking past for a century. For a long time, this remained a beautiful idea with no way to test it, the kind of thing physicists would raise over coffee and then set down. But in 2025, something happened that dragged it toward the edge of testability, and it came from the most powerful telescope we have ever built. Astronomers using the James Webb Space Telescope looked at a field of hundreds of distant galaxies and did something simple. They asked which way each one was spinning. In a universe with no preferred direction, which is what we have always assumed we live in, the answer should be a coin flip. Roughly half the galaxies should spin one way, roughly half the other, with no overall bias, because there is no reason for the cosmos as a whole to favour a direction. That is not what they found. In the sample of 263 galaxies studied by the researcher Lior Shamir, about 2/3 were spinning one way, and only about 1/3 the other. A clear lean, a preferred direction, written into the rotations of galaxies across the sky. And black hole cosmology predicts exactly that. Because if our universe was born inside a rotating black hole, and almost all black holes rotate, then it should have inherited a direction from its parent, an axis, a leftover spin from the thing it formed inside. A universe that is the interior of a spinning black hole would not be perfectly even-handed about direction. It would carry the fingerprint of its parent's rotation. And a 2-to-1 lean in how galaxies spin is the kind of fingerprint you might expect. I want to be careful and honest here, the way this subject demands, because there is a competing explanation, and the same scientist who found the asymmetry was the first to name it. It is possible that the lean is not a property of the universe at all, but a distortion introduced by us, by the fact that we are observing from inside a galaxy, the Milky Way, that is itself rotating. Our own motion might be subtly biasing which spins are easier for us to see, tilting the count without the universe being tilted at all. If that is the answer, it is less dramatic, but it is not nothing, because it would mean we have been misreading the distant sky in a way we had not accounted for, and would have to correct. So the finding sits there, genuinely unexplained, pointing to either a universe with a built-in axis or a flaw in how we read the heavens. Either way, the sky came back not quite even, and we do not fully know why. Let me take you to the edge, so you can feel what being inside really means. Imagine you set out to find the outside. You have all the time and speed you could want, and you decide to reach the boundary of the universe and look over it. You travel toward the farthest galaxies, and as you go, something maddening happens. The galaxies ahead of you do not get closer. The expansion of space carries them away faster than you can approach, sliding them toward the horizon, and the horizon itself stays exactly as far ahead of you as it was when you began. You push harder, and the universe simply unrolls more of itself in front of you, always keeping the edge at the same untouchable distance. There is no wall you arrive at. There is no rim you peer over. There is only more inside and then more inside, and the growing understanding that you are not travelling toward a boundary at all. You are pressed against the inner surface of one, a surface you can never reach because it recedes from everything, a surface that, like the horizon of a black hole, only ever lets things fall further in. There is no out. There was never an out. The out was the assumption. There is a reason some physicists find this picture attractive beyond its strangeness, and it is worth naming, because it keeps the idea from being mere spectacle. A good theory should earn its keep by explaining things you did not build it to explain, and black hole cosmology quietly does a few of those. It offers a natural account of the Big Bang, which in the standard picture is simply asserted, a beginning with no before and no cause. In the bounce version, The beginning is not a bare mystery, but an event. The rebound of matter that had collapsed inside a black hole in some parent universe, which gives our origin a mechanism instead of a shrug. It offers a possible source for the arrow of time, the reason time seems to run in one direction, inherited from the collapse that birthed us. And it dissolves the singularity, that place of infinite density where our equations scream and quit, replacing it with a finite physical bounce that never reaches the impossible. None of that makes it true. A theory can be elegant and explanatory and still be wrong, and most physicists remain, rightly, unconvinced, waiting for evidence that can decide the matter rather than merely allow it. But it does mean this is not idle fantasy. It is a serious attempt to answer questions the standard story leaves open, and its price of admission is only that you accept a possibility you cannot rule out, that the cosmos you call everything is the inside of something, sealed behind a horizon you were born within and can never approach. So the sixth step takes the exterior of everything and folds it into an interior, and notice how far the countdown has carried us. We started at the smooth backdrop of space, and we have arrived at the possibility that the entire cosmos is enclosed, that the beyond is a one-way wall, that there is no external vantage from which any of this could be seen whole. The fear is no longer out there in the dark has closed around us, and now the countdown makes its final turn, the one it has been preparing for all night. Because so far, however inward we have moved, we have still been talking about the universe, the container, the thing you are inside of. The last three steps stop talking about the container and start talking about you, the one who has been lying here, listening, taking all of this in. We're about to question whether your memories are real, whether you can die, and finally, whether the next moment is coming at all. And the first of those, the one waiting on the next rung down, is quietly the most destabilizing thing on the entire list, because it cannot be argued away, and because you are, right now, in exactly the state it describes. You believe that a minute ago actually happened. You believe that you have a past, that the room you're in existed before you started listening, that your memories are records of real events. You have never once questioned this, because questioning it feels absurd. Of course the past happened. You remember it. That memory is the ground you stand on when you think about anything at all. That is the seventh assumption, and it is the most intimate one yet, because it is not about space or matter or time in the abstract. It is about whether your own mind is telling you the truth. And the unsettling thing we're going to look at now is a genuine problem in cosmology, taken seriously by serious physicists. That says the most likely explanation for your entire experience, including every memory you have, is that none of it is real, and that you flickered into existence a moment ago, complete with a lifetime of recollections that record nothing that ever happened. This is called the Boltzmann brain problem, named for Ludwig Boltzmann, one of the founders of the physics of heat and disorder, who ran into the seed of it in the 1890s. Boltzmann was trying to understand why the universe is so orderly, and he toyed with the idea that order could arise as a random fluctuation out of disorder. The way, if you shuffle a deck of cards long enough, you will occasionally get a run of them in sequence purely by chance. But he and those who came after him noticed a problem with using chance to explain the ordered world we see. Small fluctuations are overwhelmingly more likely than large ones. If order comes from random chance, then a little bit of order is astronomically more probable than a lot of it. And that leads to a very strange prediction once you follow it honestly. Here is the heart of it. Producing an entire orderly universe by chance, with its hundreds of billions of galaxies, its physics that holds together, its long, consistent history, is monumentally, almost impossibly unlikely. But producing just one conscious observer, a single brain, with a single moment of experience and a set of memories, is enormously less unlikely by comparison because it requires so much less order. Not likely in any everyday sense, but vastly, vastly more likely than conjuring a whole cosmos. So if conscious observers can arise from random fluctuations at all, then the overwhelming majority of them should be lonely, isolated brains that fluctuated into being for a single instant, not observers embedded in a real ordered universe with a real history. The full universe is the hard way to make an observer. A single flickering brain is the cheap way, and nature, playing dice over enough time, should make far, far more of the cheap kind. Now bring this into the modern picture because it is not just a 19th century curiosity. Our best cosmology suggests the universe may last essentially forever, expanding into a cold, thin, nearly empty state that persists for eternity. And in a space that lasts forever, even the rarest fluctuations, the ones with probabilities so small they essentially never happen, will happen, because forever is long enough for essentially never to occur, and to occur again, endlessly. Physicists working on this in the early 2000s, names like Dyson and Kleban and Susskind and Albrecht and Sorbo, showed that in such a universe, random fluctuations of the empty vacuum would, over the eternal span, produce conscious brains. Not many at any given moment, but given eternity, an unlimited number of them. Far more than the number of ordinary observers who ever evolved on planets during the brief, early, ordered chapter of cosmic history that we think we live in, and that produces a question you cannot easily shake off once you have really heard it. If the universe contains vastly more randomly fluctuated brains than genuine evolved observers, then a randomly chosen conscious experience is far more likely to belong to a fluctuated brain than to a real person. So when you ask, "What am I?" the statistics give an answer you do not want. You are probably one of the fluctuations, which means the memories you have of a moment ago, of your childhood, of the beginning of this sentence were not recorded from real events. They assembled with you out of the dark an instant ago, false from the start, indistinguishable from real memories because there is nothing to compare them to. I want to hold you here for a moment gently, because this is one of the places tonight where the floor genuinely drops away. The thing that makes the Boltzmann brain idea so much more disturbing than any distant black hole or dying star is that you cannot step outside it to check. Every reassurance you might reach for is itself a memory or a perception, and those are exactly the things in question. You want to say, "But I clearly remember my whole life." It is all right there. And the fluctuation would say the same, with equal conviction, because a fabricated memory feels identical from the inside to a real one. You want to say, "But the world around me is so detailed and consistent." But you are only perceiving that world in this single instant, and the consistency is part of what could have assembled with you. There is no test you can run, because you would have to run it using the very faculties that are on trial. The one thing you are most certain of, that your past is real, that the moment before this one truly happened, is a thing physics cannot presently prove to you. Not because the answer is hidden somewhere you could go look, because the question closes over you completely, and you are inside it right now. So how do physicists live with this? Not by disproving it, which no one can do. They live with it by turning it into a tool. The physicist Sean Carroll made the sharpest version of the argument, and it is worth understanding because it is also the handhold backup. Carroll points out that any theory of the universe which predicts that most observers are Boltzmann brains is, in his phrase, cognitively unstable. It undermines itself. Because if the theory is right and you are probably a fluctuated brain, then your reasoning, your memories, your grasp of logic and evidence all fluctuated in a moment ago too, which means you have no reliable basis for believing the theory that told you so, or anything else. A theory that concludes you cannot trust your own mind has sawn off the branch it was sitting on. It cannot be true and believed at the same time, and so, Carroll argues, we are entitled to reject any model of the cosmos that predicts a universe full of Boltzmann brains, not because we can prove such brains do not exist, but because taking them seriously would dissolve the very possibility of reasoning about anything. The nightmare is used, in working cosmology, as a filter. A model that produces too many Boltzmann brains is thrown out, precisely because the alternative is unlivable. Sit with the strangeness of that resolution. We do not escape the Boltzmann brain by showing it is false. We escape it by deciding that any universe in which it is true would be a universe we could not think in, and choosing, as a matter of intellectual survival, to build our theories so that it does not arise. It is less a proof than a refusal. A line drawn in the sand that says, we will assume our memories are real, because we must, because reasoning itself depends on it. Which is a remarkable thing to notice about the ground you stand on. Your confidence that your past is real turns out to rest not on evidence, but on necessity. You believe it because you cannot function otherwise, and physics, at its honest edge, can offer you nothing firmer than that. It is worth being clear about why a universe would ever do such a thing, because at first it sounds like pure fantasy that a brain could assemble itself out of empty space. The key is that empty space, according to our physics, is not truly empty and not truly still. Even the deepest vacuum seethes with tiny quantum fluctuations, particles flickering in and out of existence, energy trembling around its lowest value. Almost always these fluctuations are minuscule and instantly gone. But fluctuations come in all sizes, and a larger one, while enormously less likely, is not impossible, only rare. And in a universe that expands forever into a cold, thin, nearly empty state, and then simply persists, cooling and stretching for eternity, there is no deadline. Rarity stops being a protection when you have forever. A fluctuation that would take a length of time beyond all reason to occur will, in an eternal universe, eventually occur, and then occur again, without end. And among the endless catalogue of fluctuations that eternity permits, some will happen to assemble, out of the trembling vacuum, the exact arrangement of matter that is a functioning conscious brain, holding a single instant of experience, complete with the sensation of a body and a past. Not because anything guided it there, but because given endless time, everything that is merely improbable happens, and happens infinitely often. This is what turns a curiosity into a genuine problem for cosmologists, because it forces a question they cannot avoid, the question of what a typical observer is. When we build theories of the universe, we quietly assume that we are ordinary observers, that our experience is representative, that the view from where we sit is roughly the view from anywhere a mind might be. That assumption is doing hidden work under all of cosmology, and the Boltzmann brain problem attacks it directly, because if the eternal vacuum produces vastly more fluctuated brains than the early ordered universe produces evolved ones, then a typical observer is not an evolved being on a planet at all. A typical observer is a fluctuation, which would mean that we, if we are typical, are almost certainly fluctuations too, and that everything we take as evidence about the wider universe, every telescope image, every measurement, every memory of a consistent world, is just the momentary contents of a brain that assembled a heartbeat ago and will dissolve a heartbeat from now. The ordered cosmos we think we inhabit would be the illusion, and the lonely flicker in the dark would be the reality. That is the true vertigo of it. Not that such brains might exist somewhere, which is strange but bearable, but that the counting seems to say you are more likely to be one of them than to be what you feel yourself to be, and that there is no observation you could make from the inside to prove otherwise, because every observation is exactly what the fluctuation also has. That is the seventh thing set down. Not the permanence of matter, not the existence of an outside, but the reality of your own memory, held now not by proof but by a decision to keep going. And having questioned whether your past is real, the countdown turns to something even closer to the bone. It turns to your ending, to the one certainty everyone carries, the one fact about the future that no one doubts, that someday you will die. The next idea does not comfort you about that. It does something far stranger. It suggests that from the inside, you might never get to. There is a version of quantum physics taken seriously by a great many working physicists in which you cannot experience your own death, not because you are immortal in any comforting way, but because every time your life should end, there is always some branch of reality in which it does not, and your awareness only ever continues along the branches where you are still alive. From the inside, the door to your own ending never quite closes. You keep finding yourself, against all odds, still here. That is the eighth assumption we set down, and it may be the one you would least expect to have to defend. You do not doubt that you will die. It is perhaps the only thing about the future you hold with complete certainty. Everyone dies. It is the one appointment no one misses. And the idea we are going to sit with now does not deny that you will die in the world as others see you. It questions something subtler and stranger, whether you, from within your own stream of experience, will ever actually arrive at the ending. And it grows directly out of one of the most respectable and widely held interpretations of quantum mechanics we have. To get there, we have to talk about what happens when a quantum measurement is made. In the world of the very small, particles do not have single definite states until they are measured. An atom can be poised between decaying and not decaying, a particle between spinning one way and the other, held in a blur of possibilities. And then a measurement happens, and you get one definite outcome. The question that has haunted physics for a century is, what happens to the other possibilities? Where do they go? In 1957, a physicist named Hugh Everett gave the boldest possible answer. They do not go anywhere, he said. They all happen. At every quantum juncture, reality divides. The universe branches, one branch for each possible outcome, and every branch is equally real. This is the many worlds interpretation, and it is not a fringe fancy. It is one of the leading ways physicists make sense of quantum mechanics, held by a substantial number of serious people, because it takes the equations at face value and adds nothing to them except the willingness to believe they mean what they say. Now take that idea, that reality genuinely branches at every quantum event, and follow it into a place its own authors found hard to look. It was laid out as a thought experiment by several thinkers independently, Hans Moravec in 1987, Bruno Marchal the following year, and then formalized most sharply by the physicist Max Tegmark in 1998. They imagined a device rigged so that its action depends on a single quantum event, a coin flip at the smallest scale of nature. If the particle goes one way, the device does nothing. If it goes the other way, the device ends your life instantly. And because it depends on a quantum event, the many worlds picture says the universe branches every time it is triggered. In one branch, the particle spared you, and you live. In the other, it did not, and you are gone. Here is the turn. In the branch where you died, there is no more experience for you. That version of your awareness simply stops. But in the branch where you survived, your experience continues, unbroken, as if nothing happened. And you can only ever find yourself experiencing the branches in which you are still alive, because the branches in which you are dead contain no you to do any experiencing. So trigger the device again. Again it branches, again one version of you dies and one lives, and again you find yourself necessarily in the survivor's branch, because that is the only branch your awareness can occupy. Do it 100 times, do it 1,000. In the world outside, in almost every branch you are long dead, and the people watching held a funeral. But from the inside, from the single thread of experience that is yours, you have survived every single time. Because the only branches you were ever able to experience were the ones where you lived. The improbability piles up to a mountain, and you feel none of its weight, because you're only ever standing on the one path that made it through. Let me take you inside that room, because it is the only way to feel the specific horror of it. You're sitting in front of the device. You understand exactly how it works. You reach out and you trigger it, knowing that in this instant reality is splitting, and that in some version of the world this is the last thing you ever do. You hear a soft click. Nothing. The particle went the safe way and you are still here, your heart still going, faintly surprised. You trigger it again. Click. Nothing. Again. Click. Nothing. You begin to lose count. Every time, without exception, the harmless outcome, the click of nothing, over and over, far past what any luck should allow. Somewhere, in branch after branch you will never see, versions of you are ending one after another, but you do not experience those. You cannot. You only ever experience the improbable, unbroken survival, the click that keeps coming, the impossible good fortune that from the inside does not feel like fortune at all, but like a door you keep expecting to close that simply, quietly, will not. You are still here. You are always, from your own point of view, still here. It is worth pausing on how directly this grows out of the most famous puzzle in all of quantum physics, the one with the cat. You have probably heard of Schrödinger's cat, the thought experiment in which a cat in a sealed box is, according to the raw equations, left in a blur of alive and dead at once, until someone opens the box and looks. Schrödinger invented it to show how absurd he thought the situation was, how badly the quantum description seemed to fail when you scaled it up to something as large and definite as a living animal. But the many worlds reading takes the absurdity and simply accepts it. It says the cat really is both, that the box contains a branching, one world with a living cat and one with a dead one, both equally real, and that when you open the box you do not collapse the blur, you merely discover which of the two branches you have become part of. The quantum suicide experiment is nothing more than Schrödinger's cat with you placed inside the box, cast as the cat rather than as the person who opens it. And that single move, putting yourself in the box, changes everything, because you can be the cat in the branch where it lives, but you can never be the cat in the branch where it dies. From inside the box, the lid only ever opens on survival. Now sit back and feel where that goes if you extend it past the thought experiment to life itself, because that is the truly unsettling reach of it. Your life is full of quantum forks and full of moments where you might have died and did not. If awareness only ever continues along surviving branches, then no matter what threatens you, there is always some thread, however improbable, in which you pull through, and that is the thread your experience follows. Taken to its limit, you would never subjectively reach your own death. You would thread survival after survival into extreme old age and then past it, always finding yourself, impossibly, still alive in an ever more improbable and ever more frayed condition. Immortality not as a gift but as a sentence. Not a bright unending life, but an inability to ever get to the end, no matter how much you might by then want to. I want to be careful and honest, because this idea is often told in its most lurid form and left there, and the honesty is important. Even Max Tegmark, who formalized the experiment, does not believe it delivers real immortality in the actual world, and his reason is worth holding on to as we climb back up. The thought experiment assumes death is instant and binary, a clean switch from fully alive to fully gone in a single quantum instant. But real death is not like that. Consciousness fades. It dims by degrees, through injury and illness and the slow failure of the body, and there is no sharp quantum fork where you are wholly here one instant and wholly gone the next. In the real world, you can slide gradually down into diminished states and out the other side into nothing, with no magic branch that keeps your full awareness intact. So Tegmark himself concluded that you should not expect to live forever. The horror survives only in the idealized version, the clean instant death machine that does not exist. In the messy real world, the door does close, and yet, even softened, something about it refuses to fully settle, and it is this. No experiment could ever rule it out, because the idea, by its nature, makes no prediction anyone on the outside could check. The only evidence that would ever confirm quantum survival is evidence available solely to the one who survives, and that person could never share it, and could never even be sure it was not luck. It lives permanently in the blind spot of what can be tested, a possible feature of a serious theory that can be neither confirmed nor denied, only reasoned about in the dark. That is the eighth thing set down then. Not the reality of your past, which we questioned a moment ago, but the finality of your future, the plain certainty that your experience will one day end. Physics cannot even promise you that cleanly. It hands you back a strange, unfalsifiable maybe, and lets you sit with it. It is fair to ask how seriously to take an interpretation that leads somewhere this strange, and the honest answer is that many worlds is not a fringe position a few eccentrics hold. It is one of the major interpretations of quantum mechanics, favoured by a substantial number of respected physicists, precisely because it is in a sense the most conservative reading of the equations. The mathematics of quantum theory describes systems as evolving into combinations of all their possible outcomes at once, and every interpretation has to explain why we only ever see one. Most interpretations add something, a special rule, a collapse, an extra process that reaches in and selects a single result and throws the rest away. Many worlds adds nothing. It simply says the equations are complete and mean exactly what they say, that all the outcomes are real, and the branching is real and nothing gets discarded, and that the appearance of a single result is just what it feels like to be one branch among many. That refusal to add anything is why serious people hold it, and it is also why the immortality argument cannot be waved away as science fiction, because it follows from taking a mainstream interpretation at its word. The place it finally breaks down is not in the branching but in the assumption about death, and in one more thing worth naming. Even if quantum survival were true, it would be the loneliest fact in existence, because it could never be shared. The version of you that keeps surviving could never prove it, not to anyone else and not even to yourself, because from the outside it looks like ordinary luck, and from the inside there is no way to distinguish having threaded a million improbable branches from having simply not died yet. The evidence would exist, but it would be locked forever inside a single unrepeatable point of view, unusable, uncheckable, a truth with an audience of exactly one who can never quite be sure of it. We have taken away a great deal tonight, one quiet certainty at a time, the smoothness of space, our safety, our ability to see a danger coming, the permanence of matter, the uniqueness of this moment, the survival of the truth, the existence of an outside, the reality of memory, and now the finality of death. 9 of the things you never think to doubt, examined and found to be assumptions rather than guarantees, and there is one left, the 10th and final step. And it is the strangest of all, because it is not about any object out in space, and it is not even really about you. It is about the one thing that every other item on this list quietly depended on, the thing so basic that we have used it in every sentence, without once stopping to wonder whether it too could be taken away. We have arrived at the last one, and I told you at the very beginning that the most terrifying theory on this list was not about any object in space at all. It was about the one thing you're most certain is still running right now, the thing you have never once thought to question, the thing so basic that you have been standing on it through every single idea tonight without noticing it was there. It is time. And the final theory, the one at the bottom of the countdown, is that time itself may simply end. Think about how strange it is that we saved this for last, and how obvious it is once it is said. Every fear we have walked through tonight happened in time. The cosmic string sweeping past needs time to sweep. The comet shower unfolds over time. Matter creeps toward iron over time. The universe returns to its configurations over time. The galaxies cross the horizon over time. Your awareness threads its survivals through time. Time has been the stage under every single act. It is the medium all the other terrors were happening in. And precisely because it was the stage, we never turned around to look at it. You never ask whether there will be a next moment. Of course there will be a next moment. There is always a next moment. That is the most fundamental of all the things you never think to doubt. And it is the one physics can least promise you. The idea comes from a paper published in 2010 by 4 physicists, Raphael Bousso, Ben Freivogel, Stefan Leichenauer, and Vladimir Rosenhaus, and its title does not hedge. They called it plainly, Eternal Inflation Predicts That Time Will End. To understand how respectable physicists arrived at a sentence like that, you have to follow them into one of the deepest puzzles in modern cosmology, and it starts from a beautiful idea that has a rotten problem hidden inside it. The beautiful idea is called eternal inflation, and it is our leading picture of how the Big Bang fits into something larger. It says that the rapid expansion that began our universe was not a one-time event, but an ongoing process, that somewhere out in a larger reality, space is still inflating, still budding off new universes, and will go on doing so forever, producing an endless number of pocket universes, of which ours is one. It is an elegant framework and it solves real problems. But it carries a poison, and the poison is infinity. If eternal inflation produces an unlimited number of universes, containing an unlimited number of galaxies, stars, and observers, then everything that can happen happens an infinite number of times. And when everything happens infinitely often, probability breaks. You can no longer say that one outcome is more likely than another, because both happen an infinite number of times, and infinity divided by infinity is meaningless. Cosmologists need to be able to make predictions to say this kind of universe is common and that kind is rare. And eternal inflation, left alone, makes that impossible. It drowns every prediction in an ocean of infinities. So physicists do something to tame it. They impose what is called a cutoff, a measure, a mathematical rule that says, we will count everything that happens up to a certain point, and we will use that finite sample to work out our probabilities. It is a bookkeeping device, a way to get finite, sensible numbers out of an infinite framework. And for a while, that is all it was thought to be, a trick of the accountant, with no physical meaning. You draw a line, you count what is inside it, you get your probabilities, and the line itself is not supposed to be a real thing. Here is where Bousso and his colleagues found the horror hiding in the arithmetic. They showed that if you want the cutoff to actually give the right answers, to match the probabilities we observe, then you cannot treat it as a mere accounting fiction. The most successful versions of the cutoff behave, mathematically, as though the line is real, as though it is an actual event in time, a moment beyond which the counting genuinely stops because there genuinely is no more. And if the cutoff is a real event, then it applies to everything that reaches it, including us. Any system that runs up against the cutoff does not continue past it. It simply stops. There is no next moment on the other side, because the other side is where the counting and the time run out. And then they did the thing that makes this more than an abstraction. They estimated when. Working through the most successful measures, they calculated how long our own region is likely to have before it encounters the cutoff, and the answer was not comfortably infinite. It was about 5 billion years, roughly the same span as the sun has left before it swells and dies. A finite, almost tangible countdown sitting inside our best theory of the cosmos, at the end of which time itself may reach its edge. When the paper came out, one science headline put it as plainly as anyone could. Time, it said, is likely to end within 5 billion years. Now I need you to understand exactly what kind of ending this is, because it is not like any of the others we have discussed. and the difference is the whole point. When we talked about the end of matter, there was still time running on in which the matter had ended. When we talked about the heat death or the iron stars, there was a cold, empty universe persisting through endless time. Every ending we have imagined tonight was an ending that happened in time, with an after, even if the after was only darkness and silence. This is not that. The end of time has no after. There is no moment following it in which anything, darkness or silence or emptiness, could be said to exist because moments are exactly what has ended. It is not a wall you hit. It is not a light going out, because a light going out is an event, and events need time. It is the quiet removal of the very possibility of a next thing. Let me try to bring you to it, though it resists being brought to because there is nothing to see. There is no scene of the end of time. That is what I have to give you instead of a scene, and it is stranger than any image. Picture yourself in this moment, exactly as you are, and now reach forward in your mind for the next moment, the way you always do, without thinking, 1,000 times an hour, trusting that it will be there to receive you. Usually it is. The next instant arrives, and you flow into it, and the one after that. But at the cutoff, you reach forward for the next moment, and there is no room for the reaching to happen. Not darkness, which would be something. Not a jolt, not a sensation of stopping, because sensations take time and there is none left to hold one. There is this moment, whole and ordinary and calm, and then there is not a next one, and there is no you left in any after to notice the absence, because the absence is not located in any after at all. You would never see it coming. And listen to what that old phrase has become. All night it has meant a threat that arrives without warning, a string or a comet or a black hole you cannot detect until it is upon you. Here, at the end, it means something final and complete. Not that you would fail to see the warning, that there would be no after in which you could have been warned, no later vantage from which the ending could ever be observed, not even by you, not even for an instant. The one ending in the universe that truly cannot be witnessed, because witnessing is a thing that takes a next moment, and the next moment is precisely what is gone. That is the bottom of the countdown. The one thing you never think to doubt, the arrival of the next instant held up to the light and found to be, like all the others, an assumption rather than a promise. Not the smoothness of space, not the permanence of matter, not the reality of memory, but the plain continuation of time, the quietest and most total of them all. And now I want to tell you why physicists, for the most part, will not talk about this, because the reason is not what a conspiracy would have you believe, and it matters. It is not that they are hiding a countdown. The paper is public, peer-reviewed, openly debated. The reason most of them set it gently aside is that they read it not as a prophecy but as a warning sign about the theory itself. When your framework predicts that time will end in 5 billion years, the most natural response is to suspect that something is wrong with your framework, specifically with that cutoff, that accounting device we bolted on to tame the infinities. Most physicists take the end of time as evidence that we have not yet found the right way to make sense of eternal inflation, that the measure is a placeholder for a better idea we do not have yet. It is a reductio, they say, a sign of a flaw, not a forecast of doom, and they are probably right. But, and this is why it stays on a list like this, no one has produced the better idea. No one has found the replacement that makes the problem go away cleanly. So the end of time is not resolved, it is filed. Set on a shelf marked, we think this means our math is incomplete, and we do not yet know how. Which is a very different thing from knowing it is wrong. So here we are, at the end of the count, and I could leave you at the bottom of it, in the dark, with the next moment made uncertain and every comfort taken away. But that is not what this was for, and it is not, I think, where the honest reading of any of this actually lands. So let me turn us around gently and walk us back up into the light. Look at what we have really been doing tonight. We have taken 10 of the most unsettling ideas at the honest edge of physics, and every single one of them turned out to be a place where the equations run past what anyone can test, where our best theories point towards something and then admit they do not fully know. Not one of these is proven. Several are probably wrong. The end of time is likely a flaw in the math. The eternal return depends on a universe we may not live in. Quantum immortality, even its own author does not believe. The Boltzmann brains are held off by a decision to keep reasoning. These are not sentences the universe has passed on us. They are the shape of the boundary of human knowledge, the exact places where we can see far enough to ask the question, but not yet far enough to answer it. And that is not a horror. That is the most extraordinary thing about us. A species on one small, warm world, lying under an ordinary sky, has reasoned its way to the end of time and the edge of the universe and the bottom of matter, and has been honest enough to say, here, right here, is where we stop being sure. That honesty is not a weakness. It is the whole achievement. Let me say plainly what all 10 of these have in common, because seeing it is part of the comfort. Every one of them lives at a place where our knowledge runs out, not where it ends in despair, but where it ends in a question we're not yet equipped to answer. The cosmic strings sit in the gap between allowed and observed. The end of time sits in the gap between a theory that works and a cutoff we do not understand. The Boltzmann brains sit in the gap between what the counting says and what we must assume in order to keep thinking at all. These are not the universe's verdicts on us. They are the frontier of what a mind can currently reach. And a frontier is, by definition, the place where the known meets the unknown, which is the most interesting place there is to stand. A civilization that had run out of terrifying theories would be a civilization that had stopped asking hard questions, that had decided the map was finished and there was nothing past its edges worth wondering about. The fact that we can generate a list like this, that a species can lie under its ordinary sky and reason its way to 10 different edges of the possible, is not a sign that the universe is out to get us. It is a sign that we are still looking, still pushing the boundary of the sayable outward, still willing to follow the mathematics past the point of comfort and report honestly what we find there, even when what we find unsettles us. That willingness is rare, and it is precious, and it is a far better thing to notice about tonight than any single one of the fears themselves. And remember the line I asked you to carry. We are alive in the last chapter that can still be read. I meant it, before, as something a little mournful about the evidence leaving the sky. But turn it over now and it becomes the opposite. We are alive in the chapter that can still be read. Not too late when the galaxies have fled and the truth is gone. Not too early, before there were minds to look. But now in the narrow, improbable window when a universe like this one is still legible, when the pages are still open, when a creature made of the very matter that is slowly turning to iron can lie in the dark and take in the whole strange story and feel it. That is not a small thing to be. That is a piece of almost unaccountable luck. So let the calm come back. The sky outside your window is telling the truth. It really is quiet tonight. Space really is, near you, right now, as smooth and safe and still as it looks. The next moment really is, almost certainly going to arrive, and the one after that, and you're going to drift down into sleep on the back of an ordinary, uncountable series of them. The calm is not a lie. It is only an edit, a gentle, partial, survivable view of something far stranger underneath. And the strangeness underneath does not make the calm less real. It makes it rarer. It makes this ordinary night, this safe and unremarkable now, into the one improbable thing that all those terrifying theories were quietly circling the whole time. You never think to notice the next moment arriving. Tonight, just once, as you fall asleep, you might. And you might find that the noticing feels less like fear than like gratitude, for the simple, extraordinary fact that here you are, and the moment came and you were awake enough to feel it.